Your clock starts now.
Good morning, everybody. Thanks for coming. I'm David Trilling. Thanks, Jake, for organizing this session. I'll start us off by talking about SNAPS, the Solar System Notification Alert Processing System. These are my collaborators. All the names in red are students who have worked on this project. Okay, what is SNAPS? SNAPS is a downstream broker that is dedicated to solar system science. Goals are the following. Number one, ingest alert data from moving objects, ZTF and LSST, maybe the other surveys as well. Two, we derive various properties like colors and light curves and so on. Number three, we identify individual population outliers. Number four, we serve this data to the community. And number five, we do science related to small bodies. I won't talk about all those today, but let me give you a few highlights. In case you just wandered in here from off the street, let me remind you how LSST data flow works. Every 30 seconds, the shutter closes. Excuse me. Transient detection is carried out. If the transient source is identified as a known solar, the question is asked, is that transient source a known solar system object? Yes or no? If no, do I have a pointer? Maybe this is my pointer. If no, then you go on this path up here, broadcast to brokers. I'll come back to that in a moment. If yes, you're on this path down here. Eventually, you'll go directly to the miner, but you also broadcast to the broker. And in this case, I've listed Antares, which is a broker that receives these known solar system object alerts and immediately passes them on to us. So we're ingesting known solar system object alerts. I want to point out that if the transient was not identified as a known solar system object, it could still be a solar system object. It just was not designated at the time of observation. We don't see it. We only see ones that have a designation as part of the alert. Okay, what makes SNAPS unique? Well, we're the only solar system dedicated broker. Moving objects, as you all know, present special challenges. And we collect and serve moving object data. And okay, and just to be really clear, I want to emphasize what SNAPS does and does not. What SNAPS does, we ingest, we derive properties, we have a value-add catalog, identify outliers. What we do not do is discover new solar system objects. That happens upstream from us. And we don't have any catalogs presenting non-solar system objects. Okay, we have a bunch of papers, various science and some architecture stuff. I'm not going to go through all those, but I do want to highlight two of them right here. One is a paper that Mike Gowanlock published now 2 years ago about population outliers. This is a plot that shows amplitude, rotation period, and H magnitude. And the orange spots are inliers and the black symbols are outliers. And the light blue, we color-coded some interesting objects. The point is not for you to do three-dimensional science right here, but just to demonstrate that we have a number of techniques that find outliers in various combinations of feature space. And you can read Mike's paper to learn more about it. The other one to advertise is Aaron Clark, who's sitting right there, who's going to be talking about active asteroids in just a few minutes. And together, those two, the first one I mentioned is really about population outliers, and this one is really about individual outliers. And you'll hear that a lot from us talking about those two different schemes. Okay, how to interact with SNAPS? Well, there's our webpage. This is what you see when you land on that webpage. And I won't tell you anything more because we're going to do all this in the broker session at 1:30 today. So come and I'll show you more about that specific thing at that time. Okay, here's the plot Jake just sent me. I got it. Thank you. So if you were in Jake's talk yesterday, you heard him talk about this plot. This is a Sloan A-star color and I-Z. And the other panel of this shows long ago data from Sloan that showed that the C, the S, and the V types all separated neatly in this color space. But this is DP2, and it's just one big blob. And Jake said it's because we have this asteroid variability that is different, impossible in many cases to distinguish and to end up with this big blob. Okay, so that inspired me, and then Henry asked some questions about that. So I pulled this. This is an object I pulled from SNAPS this morning, and LSST observed the main belt asteroid. On the bottom is time, and on the y-axis is absolute magnitude. This is an object observed in these four LSST filters, G, R, I, Z. And to Jake's point, you can see, for example, that the G-band observations, there are 3 measurements made close in time to each other here that have a scatter that's much larger than those formal error bars. And you can see there's an R-band, same thing, and I-band, and so on. And so the intrinsic variability of the asteroid is producing a larger scatter than the photometric uncertainty, which is why you have the Jake blob, which is called. So that's a DP2 problem. But in SNAPS, if I have 50 or more observations, which for many DP2 objects we don't, but in this case we do for an LSST object, we're able to compress that data and phase it, and we solve for the period, the amplitude, and the color all simultaneously. So this is now phase in hours. I covered up the rest of it. And again, absolute magnitude. We've stacked all those data so that they lie on top of each other, which allows us to derive the color, GRIZ colors. I can tell you the amplitude and the period for this object. So in principle, now if I took all the LSST objects and remade your plot, they would separate back into their color groups. I haven't done it. Okay. Here's our statistics and status as of a couple days ago. So we have a number of databases on the left, unique objects, total observations, and objects with more than 50 observations. And again, this is the one where we're deriving those value add properties. Here's our ZTF collection. So we have 226,000 objects with 50 or more observations, period, amplitude, color, and various other stuff. Here's LSST as of the moment. It's a pretty small number over here because we're early days. We're not anywhere close to 50 observations. But obviously, when we get back on Sky and routine template and all that stuff, that number is going to grow rapidly. Okay, I want to finish by talking about the community filters. This came from the Solar System Science collaboration to the project, who then came to us and said, can you guys do this? The answer is yes. There were 3 community filters that were proposed. One is an observation, look for an observation that's one or more magnitude brighter or fainter than expected. Well, I just showed you that when we have 50 or more observations, we can phase this light curve. I can tell you at any given time how bright the asteroid is expected to be, and then we can compare the observed to that prediction. So this is algorithms already done, outgoing alerts on this end of summer. Thank you. Extended PSF, Aaron's going to talk about, and color changers is a little more complicated, but we've been working on that for quite a while. Okay, so we're serving LSST alerts. We're serving ZTF alerts. We have a how-to document on the archive. And we're looking ahead to adjusting other streams. SNAPS is the only solar system, dedicated solar system broker. We detect individual and population outliers. And I have SNAPS stickers. Come see me after the session. Thank you.
We have time for maybe 1 or 2 questions.
Thanks. Just a question, you might be answering this tomorrow at the brokers session, but is the API or a way of doing bulk downloads available yet?
We'll talk about that in the brokers. The API is internally functional, but not externally facing yet.
I think the last time I looked at snaps, there were no images. Can you talk about that?
There are postage stamps. Come to my talk in the broker session. I'll show you.
I think that's all we have time for, but reach David after.
I'll be right there.
Yeah. Let's give David another round of applause. Hey everyone, I'm Jake. Got, I think, a conflict of interest on the time here, but that's okay. I'm going to be talking today about the main belt distribution of variability as measured by DP2. Apparently this is the Jake blob. I hadn't had that named before, but the color families that we would like to see when we measure asteroid colors from DP2 are smeared out by the non-simultaneous and not statistically large enough to smear out variability number of observations we've got in DP2. So what can we do about it? Quick show of hands. Who cares about asteroid colors in the room? Okay, great. Who cares about asteroid shapes in the room? Yeah, okay. So hopefully this is doesn't need too much justification, but asteroids have shapes. On the left is an asteroid we have a lot of data about. We know what its shape is. In the middle is a Rubin First Look asteroid, a super fast rotator that Green Street showed was a very interesting object, and we get shape constraints out of that. But most DP2 objects look something more like what we have on the right. Here we've got a bunch of objects, a bunch of observations of a single object. This object is clearly variable, and if you tried to guess the color, the G minus R color of this object from this plot on the right, I think you would have a pretty hard time. As David said, we will eventually get a lot of data, and for a whole bunch of objects, we won't have to worry about the case on the right. But I propose that there will always be more objects that we can measure the variability of than that we can measure the colors of. And so we might as well do some cool statistics and try to work out the distribution of asteroid shapes, even if we can't get a single object's precise shape from its data alone. So let's say that we only had 2 measurements per object, 2 absolute magnitude measurements per object in the same filter. Absolute magnitude number 1 is measured from an apparent magnitude and a known orbit and phase slope, and a second measurement in the same filter. We can expand that out into true absolute magnitude plus the variability at one time plus our measurement uncertainty minus the same thing for our second observation. Assuming that we know the orbits and the phase slopes really well, we can rearrange to get rid of the absolute magnitude if our uncertainties are Gaussian, and they combine nicely. And if we make one more big set of assumptions, let's say that all light curves are sinusoidal. This probably isn't true, but let's say it for now. Then I think we can express this difference in variability just as the randomly sampled difference between 2 points on a sine wave, assuming our observations are far enough apart in time that the phase of the asteroid isn't necessarily correlated with between the 2 observations, and assuming the pull of the asteroid is vertical, which I think for small enough asteroids, I think we can assume is true from the York effect. So given a couple assumptions, which later will turn into slices on our data, I think we can model the distribution of measured variability for all objects that we have at least 2 observations of in the same band, just with random samples from light curves. And you can change out the sinusoidal model into some other fancier shape at a future time. So what does this look like in DP2? Here are, I think, 170,000 objects for which we have at least 2 I-band measurements in DP2. Here is a distribution. For objects with more than 2, I chose 2 that are at least 2 days apart randomly. And here is that distribution. So most pairs of I-band measurements from the same object are less than 0.2 magnitudes apart, but there's a long tail out here into the over magnitude apart zone. So let's now assert a underlying distribution of asteroid shapes. I like Gaussians, they're simple. This is one Gaussian centered on 1 with a sigma of 0.3. And if we plug that into our previous equation and take our empirical uncertainties, we would expect a measured distribution of asteroid uncertainties that looks like this. This does not look like the blue, and so our model does not look like our data, and we can reject the hypothesis that the intrinsic distribution of asteroid variability looks like a Gaussian centered at 1 with sigma of 0.3. And you can do this a little more rigorously with a hypothesis test, and I did, and in 0 out of 10,000 cases did they look anything like each other. So the strongest result I can give is a 4 sigma rejection, and I did. What if we try something else? This looks a little better. Mu of 0.2, sigma of 0.1. Visually, it looks a little better. Still rejected 10,000 times out of 10,000. We've got 170,000 data points, and so you have to have 2 distributions really look quite similar before you start getting p-values above 0. What if we try a grid of Gaussians, where this is a 40 by 40 grid over a bunch of sigmas and a bunch of mu's? One time, I get just a 4.5 sigma rejection, but in all other cases, it's completely rejected. So I can't find any Gaussians that make the previous thing look right. So let's look at a new distribution, the exponential exponential distribution dies off as an exponent. And I don't think this is standard, but I'm giving it a horizontal offset. So this is now a 2-parameter exponential starting at some minimum value. All of a sudden, there are some parameters for this distribution that are consistent with our data. So I chose one random one, not a particularly good one, but a lambda and a b for an exponential. They're right in the middle of that oval shape. And this is what we get. So suddenly we have a model that looks more consistent with our data. The hypothesis test stops rejecting this. So I think through this method, we can start to get at the underlying distribution of asteroid shapes, even with very poor per object data, as long as we have a whole bunch of objects, which Ruben has given us, and a model for what our uncertainties and what their variability should look like. Okay, so I want to constrain underlying distributions with very easy to characterize observables, like the difference between two absolute magnitudes. Next steps, we should do better data selection and really make sure that the slices that we make on our data support our assumptions. Could probably choose better hypothesis tests and produce an actual best fit model. Love to say, here's the distribution of main belt asteroids under this size. And then we should start doing subpopulations. Are red asteroids differently shaped than blue asteroids? What about the G absolute magnitude minus I absolute magnitude distribution? Can we get at the joint color shape distribution without actually fitting individual colors and shapes? Same thing, adding phase slopes, same thing, adding whole obliquity distributions. I think this is a good way to get at the underlying distributions. All right, thank you. We have time for 2 questions.
What does the exponential distribution physically mean in this case? Like what?
There's a lot of pretty round asteroids that have a axis ratio something like 0.9, and that there's a few really elongated ones. I don't have like a physical process that creates exponentially distributed sizes, but means a lot with pretty circular but not quite circular, and then small number width.
How many observations does it take for you to get a phase slope?
So because these asteroids are all measured at different phase angles, I don't think you need a phase slope per object.
Okay.
I think you can still do it with 2 observations
Okay.
because you have a distribution of separations of phase. You have 170,000 points. Now, I don't want to, there's already degeneracy in a 2-parameter model. So maybe we need to add more observables, maybe 3 or more, but like you could constrain a higher dimensional space with just this. You would just have an oval and more dimensions that would probably be bigger. I still like the idea of it. Mario, and then that'll be it. We'll move on to our next speaker.
I'm just going to throw a semi-useless comment, which is that thank you for bringing small body science into the area of cosmology, because I always miss banana plots and contours and statistical estimates from that area. So like we're there.
We should do like 1 plus lambda and like omega sub b instead of lambda and b. Make it look more.
To make those parameters maximally confusing.
Okay, that is all for me. Our next speaker is Aaron Clark.
You have a question on Slack.
Oh, I will answer the question on Slack. Really, on Slack or on Zoom?
Slack.
Right.
Start.
Yes.
Okay. Hi, everyone. I'm Erin. I'm going to my 3rd year of grad school at Northern Arizona University. I work with David Trilling and the SNAPS team, and I'm going to talk to you today about some of the work we've been doing to identify candidate active asteroids in the LSST alert stream. I'm not going to go into too much detail about SNAPS because you just heard from David, but essentially it's a downstream alert broker to Antares that ingests and derives physical properties for solar system sources. And you're looking at that data flow on the right-hand side from ZTF, LSST surveys to Antares to SNAPS. There's this left-hand side that is some daytime analysis, but the work I'm going to talk about falls under this real-time nighttime analysis window that ingests and analyzes as the alerts are coming in. So the active asteroids, they're cool. They're objects that look like comets unexpectedly or maybe not. And they're driven by multiple mechanisms, each of which inform important things about solar system formation and evolution. I'll highlight that the sublimation-driven ones or main belt comets are especially interesting because some of them seem to be driven by water, which separates them from the comet population. And so that kind of suggests if we can constrain the MBCs, maybe we could say something about the abundance of water in the asteroid belt. And as well, maybe their potential roles in delivering materials contributing to the origin of life on Earth. Very cool. So this is MBC 433P in the ZTF alert stream. You can see it's got a nice bright tail right there. And we're going to look for them in LSST. So current estimates are 1 in 10,000 for the occurrence rate of these things. And there's less than 100 known, so it's a pretty small sample size. LSST presents a really great opportunity for us to increase the sample size because the sample of known asteroids in general is going to essentially multiply by 5, which is very exciting. These are large data volumes, though, we've never faced before as a community. And so the common theme with all the talks this week is automated candidate selection. So we've kind of landed on two efficient methods at finding the cometary coma or tail that we're talking about, that morphology, PSF comparison and machine learning. I'm going to start with PSF comparison first. So each LSST exposure is going to have around 1,000 solar system sources in the exposure. We can create a distribution of all those PSF measurements for each source and calculate the location on a Gaussian distribution of each of those measurements and a corresponding probability. This is the Z-score. That's what you're looking at on the left-hand side. So on the x-axis is PSF Z-score. On the y-axis is all the sources in one LSST exposure. You can see that there's a couple thousand there. And then there is an object that is significantly deviating from the mean. And so it's an outlier. It's a broader full width half max. It's beyond 18 sigma. And you can see it's broader and it has an asymmetric morphology. So that is what we are targeting with this tool. In tandem with that, we're using machine learning. So supervised machine learning in the form of a convolutional neural network. These algorithms are pretty good at identifying complex morphologies in image data. So we train a binary classifier, pretty simple, on a true and false class. So an inactive class and an active class using ZTF comets and known active asteroids. So that's what you're looking at on the right-hand side are two comet classes. Inactive, false is a point source. Active, true is a comet, as you can see. So prototype models have performed ranging from 80 to 97%, and that's because I'm changing the architecture of the CNN slightly and the input training classes. So the output from this is a confidence score or probability of either class. We append all the true active probabilities. That's a probability that the source is active. If we combine that probability with the probability from the PSF comparison test, we can get a total confidence that the source is actually active. I'll remind you that we're getting about 1,000 asteroids per exposure every 30 seconds. And this pipeline runs locally on my computer in less than 30 seconds and on more than 1,000 asteroids. So we can keep up with that. And then I will show what we've gotten really amazing at finding with the early LSST alerts. Before I knew that we needed a geocentric distance cut, here are the near Earth asteroids that we seem to be very good at finding. They're moving really fast on the sky plane. And so they are trailed in the images and it's a Comet adjacent signature that we can find. And then, as we all may or may not know, the image quality is pretty variant with LSST so far. It's going to improve with time and has been improving as of recently. So we're kind of getting tricked with poor focusing in this pipeline. And it's kind of hard to say what's going on with some of these objects that are getting flagged because all of the sources in the image kind of look like that. So looking forward to keeping an eye on these. So where are we going with this? We're gonna push candidates to you all for telescope follow-up. So please follow up the targets. And we're in the process of connecting that stuff that I just described to our SNAPS website. So we'll have nightly candidates for you all to look at soon. I'm going to train and refine that CNN as LSST data comes in to adapt the model to LSST. And I also want to mention that we're doing this for ZTF already. Come talk to me if you're interested about it. I've done a lot with that. And then I want to remind everyone of the overall science goal again. We're going to increase the sample of known active asteroids, and we're going to enable those population level studies and hopefully constrain the abundance of water in the asteroid belt. I'm going to leave this up and take questions. Thank you.
Thanks, Aaron. When you're doing the machine learning versus just the PSF cut, how do those samples like compare? Like, are you finding the same things? Or are you finding different things?
The separate tools, different
with
things.
the different tools.
Yeah, so the PSF comparison is really great at finding coma morphology, but it will lose like faint tails. And so the idea is to also keep the outputs from the separate tools so we can find those faint tails, which are more strongly found with.
Has a question in the chat as well.
Related, is the PSF fitting an input into the machine learning, or are they completely separate?
No, it's not so that was before I discovered that you could have like metadata features in a model. So I just take the outputs and do the same thing. But no, they're separate. And I don't measure the PSF myself. They come in the alert packet.
Yeah, so Lynn has a question in the chat. Do you have a timeline of how frequent the poor focus detections are? So she's hoping that they were significantly less frequent since end of April compared to earlier.
Can you repeat the first part of the question?
Do you have a timeline of how frequent the poor focus detections are?
Actually, I just ran this pipeline on the last night. I think it was around the 9th of July. The images looked much better, so I'm very encouraged by that. I think it's getting better. That is, I'm not affiliated with Rubin at all, so I don't actually say anything about that.
We have time for another question if there's another on the back.
Is there anything that Rubin can do to make your life easier in terms of adding more metadata or data products that you're struggling with? Like what works and what doesn't?
So for LSST, I was able to do the full with half maximum that was produced in the alert packet for ZTF, but LSST doesn't produce that actually. They produce a PSF chi-squared, so that's what I'm using. So if I have any requests, maybe a full with half max.
So basically PSF, more PSF parameters in the alert packet. All right. Thanks. That's very useful.
There might be things
There might be things I
It
could
might
do.
not be exactly, but I think we should talk about
Yeah,
it.
let's talk about it. Thanks, everyone.
Thank you, Aaron. Next up, we have Dima talking about Rubin rocks.
Yeah.
Statistical analysis of linear dynamic.
Okay.
Radius.
Let me use your camera.
Hi everybody, I'm Dmitry. I'm a postdoc at the University of Washington. I'm glad to present our project, Rubin Rocks. statistical analysis of near objects' dynamical histories. I'm going to skip this slide about what near objects are to save some time. Sorry. The thing is that near objects, they cannot stay long on their orbits. So in general, 10, 100 million years, something happens to them. So they either being ejected from the solar system or hit the sun, maybe some planets. But our solar system exists for more than 4 billion years. And we still see them, so that means there must be some source of them. And yes, they do come from the main belt, from several regions of the main belt, which are mostly associated with resonances of some planets, Jupiter and Saturn. But that actually means that these near objects, they are the probes of that parts of the main belt. Right now, we know about 40,000 near objects, and LSST should hopefully triple that number, right? So that's going to be really good. About our project. So since near object is a probe of some part of the main belt region, that means once you study this object, it's kind of like you're studying that region of the main belt. And it's much easier to study something which is passing by you and not which is very, very far. So that's why this information of where they came from can be really valuable. And so for our project, we provide two complementary approaches. So one is a fast approach, it's a statistical approach. So you just query the already pre-computed statistical dynamical evolution of near objects via our web service and API, which is still under active development. Or if you need like more precision, then we give you a new integrator. And you can take this one and integrate the orbits yourself. Of course, it's going to take you much longer time compared to the statistical approach. But if you have a unique, not typical object, maybe actually you're required to do so because the statistics is still mostly working on typical objects, not atypical. About our web service. So you go to a website, you put the orbital elements of your beloved asteroid, so some symmetry axis, eccentricity, inclination, even the uncertainties of these numbers, and it's going to give you all this information, such as the regions of where it might come from, with the probabilities for each of the region, also even with the uncertainties, some residence time when it probably entered the New York region. In the future, we would like to add additional things like time when it's spent in each class of New York. Maybe was it at some point captured in mean-motion resonances? What are the possible end states for this asteroid? So because some have more chances of colliding with the Earth, some have more chances of being ejected from the solar system. So all these kind of things. And it's very good if you have like one, your best asteroid, right? So maybe several, but if you have 100,000 of them, well, yes, it's going to be not really productive putting all this information in the web service. For this one, you need an API, and we provide this one as well. There's a QR code actually you can scan. It's going to give you the README file with all the links. So imagine you are an observer and you have 100 objects, list of 100 objects that you can observe, but you have the ability to observe only one or two. So in this case, you just query the API, see, let's say, what regions these asteroids came from, select the ones that you're mostly interested in, and observe this one. That's like our idea how it can be used. And I did get an update 2 days ago that right now the API, you can send just the designation of the asteroid, and it's going to automatically query the NASA small body database, get the orbit, the covariance matrix of it, and compute all this information. Hopefully it's not going to break anything because it's still like querying another API. We'll see. For the second approach, it's a numerical integrator. A new one, it's not a symplectic integrator, what in general people use for long-term propagations. But we modified this integrator to preserve the accuracy, and it's actually pretty good for long-term integrations. I will show you the test later. We use the quadruple precision to keep the state vectors, and the integrator, it has different orders you can choose, and up to 30. Just for the mathematicians, this is not 30 factorial, this is just for so our optimal choice is actually 14. I think it's pretty good, at least for what we are doing for integrating the asteroids. It has adaptive time steps. So once the asteroid is coming close to some planet, of course, the time step should be decreased. And so the integrator is doing it automatically, no problem. And we put a special treatment for closing address as well. So we limited the time step so that we don't miss some possible collision. And also the good part that there's no restrictions of what forces you want to add there. It's no dynamical, but you want to include relativity, no problem, non-gravitational forces, Yarkovsky, go for it. So we did test this integrator, made many tests. Of course, I don't have time for present all of them, and it's probably going to be boring. So I selected this two. Imagine you have the solar system planets, 8 planets, and then you integrate many asteroids with this. Let's say 50. Okay, it's not many, okay, it's 50. And you integrate for 1 million years. So first thing, you can check that the total energy of the system is preserved. And you can see it on the left plots. So our integrator LORB is this one. We compare it with two well-famous WHFAS and IS-15 integrators. So WHFAS, unfortunately, is not that accurate. IS-15 is better, but it's twice slower than ours. So I think it's pretty good in terms of our integrator. But I do like this second test more. So see if you take different set of 50 asteroids and then make this different 25 sets of different asteroids. The planets, they're supposed to go to the same paths because they don't care about asteroids at all. But it's numerical integration, so of course they're going to diverge in our reality. But so we think that the spread of this divergence for the planet's position can tell us something about the accuracy of our integrators. And so our integrator is this one. For different planets, this is how the maximal spread will get in 1 million years. But look at Jupiter. So after integrating for 1 million years, the consistency is 1.5 kilometers. And I think it's pretty great. Sorry, I don't have time, but we do want to use this integrator to study how the near objects become the Atira families, and also the subclass of Atira family, which is completely inside the orbit of Venus, which I cannot pronounce this class. So, thank you for your attention.
We've got time for 2 questions. Of course, I'm interested in the integrator. So it's impressive that it's basically twice as fast, but you're using quad precision.
So we're using double precision for everything except for keeping the state vectors.
Okay.
So, and that's why it's basically almost same computation time.
Okay.
But it actually helps us a lot for particular random errors.
Okay.
So just that. So brief continuation of Matt's question. So is keeping state in quads what allows you to have, let's say, this precision on the slide? Is that maybe mostly where it comes from?
I think so, yes. Because in general, so when you integrate, you have some, you have the state vector and you have plus something right at each step. And this plus something in general is smaller than this state vector. And so when you keep it in quadruple precision, you're basically saving a couple of digits. And it's probably a couple of digits. Maybe this is this couple of digits for Jupiter.
Very nice.
Okay. Then let's give Dmitry another round of applause. Next, we have Rushina, presenting an automated 3-method asteroid rotation period pipeline for Rubin first look data. And after this, we'll transition to the virtual talk.
Hello everyone, my name is Rushi and I'm a high school student from Toronto. And today I'll be talking to you guys about a pipeline that I've made to be able to find the rotation period of asteroids in the Rubin First Look and DP2 data. So the challenge is that as the Rubin telescope begins its full-scale observations, we'll be getting data for millions of asteroids. And that makes it completely unfeasible to be able to manually look at millions of light curves to see if we can find any reliable rotation periods. So that's why I created Atlas, Asteroid Time Domain Light Curve Analysis for spin tracking. And what I did is I looked for asteroids where there was enough data and where we had good enough data to be able to reliably find these asteroid rotation periods. And through there, looked for high confidence periods. And so far, I've tested it on the first look data as well as data from the DB2. So to do this, I used the Asteroid Institute database, which has the MPC replica, which I queried using the Google BigQuery. And for all of these asteroids, so I start with about 7,000, and then I filtered them, saying that I needed at least 2 filters with at least 30 different observations. And after that, I applied geometry corrections because asteroids are always moving. So I benchmarked them at a fixed distance as well as a viewing angle. And then finally, I applied 5 sigma clippings to remove any extreme outliers. So that narrowed it down to about 5,000 asteroids. So to find the rotation period itself, I used 2 different types of methods. So first, I used a sinusoidal model through both the multi-band Lobsgargle, which is able to take in data from different bands, and I used an order 2 fit. And I also used a high order Fourier using orders 2 to 4 and finding the best fit periods for each orders, and then only using a higher order if it was significantly better than the lower order. And the advantage of these higher orders is it's able to pick up more of these asymmetrical curves. And then going on to a completely different direction, I used a model that does not take into account any sinusoidal patterns. I used the PDM method, or phase dispersion minimization, which basically divides the data into bins and basically tries to minimize the scatter in one bin compared to the scatter in the overall data set. And through there, I found a rotation period this way. And by using both sinusoidal and non-sinusoidal methods, I tried to bias the algorithm the least possible. And for this, in this plot, you can see I used the example of the asteroid 2025 ML17. And you can see for all 3 methods, they were able to get the same rotation period within 1%. So from there, I narrowed it down to about 1,200 asteroids. Next, I used quality gates. So to have a reliable rotation period, I needed it to have a good phase coverage of about 80%. I needed the signal to be significant in all 3 methods. And I also needed the amplitude signal to noise ratio to be significant, which meant that the amplitude had to rise way beyond the error bars. And then finally, the period had to be well constrained. So you can see in the case of ML17, it had a very good phase coverage, and the signal was dominant across all 3 methods and had a very high signal to noise ratio, which is why my model classified this as a high confidence. So I first validated my method by applying it to data from known asteroids with already known rotation periods. For example, you can see here asteroid 58693. And all 3 of my models was able to find a rotation period of 3.04 hours. And validating this with the light curve database, I got the same rotation period. Next, I made a comparison with the Greenstreet et al. Published results. So I looked at 74 of their asteroids, and out of them, 47 of them, my model classified as high confidence, so I was able to get a reliable rotation period. Out of those 47, 33 of them, Greenstreet et al. Had found one unique solution, because occasionally they found 2 different solutions between their different models. And out of those, 32 out of 33, so about 97% matched. And among the solutions where Greenstreet et al. Found two different solutions, I found a full match with at least one of the two solutions. So I'm going to first now bring you through a few cases. So the case one is where both my model and the Greenstreet model had the same period, and we're both confident. So you can see this is the case, for example, with 2025 and with 35. And you can see all three of my methods agree, and they agree with the Greenstreet data. A second case, which I found interesting, is where my model was able to commit to one rotation period, whereas the Greenstreet et al. Was split between two different periods. So you can see I was able to narrow it down to a period of about 10.5. And this was matched through all three models. Third case is if we look at the opposite direction. So my model was not able to find a unique solution. My PDM model found a different solution, and therefore my model classified it as a low reliable solution, whereas the Greenstreet model was able to find one unique solution. And the final case is in some asteroids, we don't have enough data, or there's too many aliases to be able to pick between one solution. So in this case, both my model and the Greenstreet model was not able to pinpoint one unique solution, which shows how for these asteroids, we're simply not yet ready to find a rotation period and we need more data. So moving on beyond the 74 asteroids, I plotted to the full data set in the first look and the DP2. And here I've shown some examples of my high confidence levels that have no prior published periods. So for context, out of the about 5,000 asteroids, which I attempted to find a period, only about 10% I found a very reliable period. And you can see two examples here from the DB2, as well as two examples from the first look. I also took a look at ultra-fast radiators. So the Greenstreet et al. Paper had found 3 of them, and all 3 of them I was able to recover using my model. And in addition, I found a few extra ones in both the DP2 data as well as the first look, which are still pending confirmation. And all of this data I put as open source, and it's online on the website atlas.modernriselab.com, which I'll also have a QR code at the end. But here I have basically the rotation periods for all of the 5,000 asteroids and what I got from each different model. And in addition, I have a curve where you can actually try fitting different periods to see how they match, as well as all of my secondary data. And in addition, out of these 500 asteroids, I also conducted some population studies, looking, for example, at the rotation period. So you can see I was able to find that most of these asteroids had a higher rotation period than the spin barrier of 2.2 hours, though there were a few of them that went lower, like the fast radiators. So in conclusion, my model was successful in creating a completely automated pipeline without any human intervention that can find reliable rotation periods for asteroids. In the future, I plan to include phase curves as we get more data from different viewing geometries to be able to get more accurate absolute magnitudes. And this whole data I was able to run in about 1 day on a home computer. But I'm always looking for more computing power, especially more cores, as the Rubin data becomes higher. And I'd like to end off by saying I'll be applying to universities in a few months, and I'm open to any suggestions for undergraduate programs where I can pursue my interest in astronomy. So with that, thank you very much.
If you go back to your case 3 slide where the model diverged, the PDM looks better. So do you think it's a good idea to make sure that the sinusoidal, like that's a gate, right? So you would say this one wasn't high confidence, but what if the asteroid is just asymmetric and PDM is doing a better job?
Yeah, that's a good question. And in this case, you can definitely see there's about 3 different peaks in the data, or even 4. And eventually, I think what I want to do is I want to also create a section where I'm merging 2 models instead of all 3 of them. For example, the Fourier and the PDM would be a very good fit because Fourier can go up to order 4, which can pick up more of these asymmetric signals, and then merging that with the PDM, which can also look for these asymmetric signals, would be able to find these. So yeah, absolutely, that's a future step.
Thank you. This is really impressive. So I've got a million questions, but I'll try to narrow it down to 2. One, do you get the same results as Greenstreet et al. For the fastest moving objects, like for these 100-second ultra-fast rotators that they found?
Yeah, for the three really fast rotators, I was able to get the exact same rotation period.
Oh, that's really cool. And then you mentioned that you need more computing power, and Rubin has these. I don't know if they're now semi-annual or annual calls for essentially allocating computing power here at the data center for useful community uses. So this may be something to look at. Talk to me later, and we'll find the right forms. And a final note. University of Washington has a decent undergraduate program, and we're famous for excellent weather. So if you're looking, come to us.
Sorry, did I see? Oh, Dimitri, go ahead.
Oh, okay.
You have the microphone.
Yeah.
Yeah. So, did I see on your slide you're Canadian?
Yes.
I have compute power for you. Because we have Campfire. Yep.
One more question from Adrian.
Yeah, thank you. Incredible work. So about that asteroid MT24, and I think that'll be related. So I checked on my stuff, and you need to have like 4 Fourier series to properly fit it, and then you're going to have a really good fit. And I would say that, be careful with the stuff what you say that you need to have. I would say that all 3 methods should give you the same result, because sometimes, especially when you have a really good light curve with really interesting features, your two Fourier series is going to give you a bad result, and that could be the reason. So when you do like this, you can basically reject the most interesting and the best of the ones. So think about that.
Yeah, that's a really great point. And for now, I focused on all 3 models matching just to be able to get the most reliable rotation periods possible. But definitely in the future, I would like to expand to be able to look more in details at these interesting asteroids.
Thank you. Okay, next we're transitioning to the online talks. Laura Buchanan is up first, talking about rafts, research announcements for the solar system. Laura, can you try sharing screen? We can see if things work well. During here.
This will hopefully be my presentation here.
Okay, we can see it and we can hear you.
Okay.
Go ahead.
Okay. Yeah, I'll just leave my camera off to save internet power. But yeah, I'll get started. So yeah, I'm talking to you guys today about rafts, or research announcements for the solar system. So just giving a quick overview of our very nearly complete system. While I have these names on the screen, I'll just take a second to do a big acknowledgement of these folks here in the bottom line who work at the CADC. And the system wouldn't work how it does or look how it is without them. So they've been like crucial to this, obviously. So kind of an introduction to start as to why do we need an announcement system. So this is like a general ecosystem of the kind of follow-up that we need for unusual discoveries within the solar system. I think this diagram was originally created by Henry Shea a number of years ago now. But through our announcement system rafts, we're aiming to cover kind of this section of the ecosystem, so the mixture of short form announcements and the opportunity for the community to discuss them. Up until now, there's been no publication system that's specifically dedicated to solar system science. So this raft system we've built has been based on community input, with the kind of initial ideas for it originally put on paper a couple of years ago at the Flagstaff Solar System Sprint. And obviously other parts of this ecosystem have been covered and will be covered today, such as I think David Trilling talked earlier about snaps. I think Carrie's talking later about stuff that will cover much of the left-hand side of this. So yeah, lots of stuff happening for the solar system. A quick overview of the main points of the system for folks who may not have seen me present on this before. So like, what are rafts? So this is a system to issue short, citable announcements relevant specifically to solar system science. The aim is for it to, it is freely accessible to the entire solar system community. So although it's built with Rubin in mind, discoveries from other surveys or just from other observations are welcome within the announcement system. And these announcements include a permanent discovery attribution via a DOI. And on top of this, via the LSST community forum, which I know has come up a number of times at this meeting and is also relevant to our stuff, but that will allow the discussion of whatever exciting new discoveries are announced on the system. The general workflow that happens within rafts as kind of an overview is the data will be submitted by the user. This data goes through, once complete, to a moderator. This is a necessary step because of the DOI section, meaning that we'd like a second set of eyes to have a quick look at everything to make sure that someone's not putting in 10 announcements saying they've discovered aliens and then getting a permanent DOI assigned to that. That wouldn't be ideal. So a quick turnaround with a reviewer of the raft, and if there's some significant issue but it still should be submitted, there will of course be the opportunity to resubmit with a quick correction. But once everything's all good and approved, it goes through with a generated DOI by the CADC, and all of its data publicly accessible. I've said at the CADC, but this is all hosted on CANFAR, which is obviously run by the CADC. The Canadian Astronomy Data Centre, which I realised I've just put in the acronym the whole time and didn't actually spell it out. And then concurrent with this is the generation of the community forum post, which allows the discussion of these announcements. Like I said, we're very nearly complete, so I put a little kind of current progress here to show that we've ticked off most of these things. We worked through the software requirements with a whole load of feedback from the community to make sure that we were hitting everything that people wanted. All of that's largely implemented with the submission workflow and the ability for reviewers to approve things, and the generation of the DOI is integrated as well. This is a screenshot of just the landing page of this announcement system with a quick summary for if someone goes on this page for the first time to make sure they know what they're doing, with the ability to create an announcement, view their in progress or published drafts, browse the general published ones, and if someone has reviewer permissions to go in and have a look at those ones that and need review. Again, just the quick bullet points of the various features. I think one which I didn't mention yet is that we include the ability to link to previous announcements. So if a comet does something interesting twice a couple of years apart, you may want to link to the previous announcement to kind of set things kind of, or include relevant announcements which have happened in the past. And this is what the kind of input form looks like, because I only have 7 minutes. I've just included a quick screenshot rather than going through the whole page. But you can include information on the various corresponding authors. If there's a collaboration that has input, that can be included. You can have the usual like abstract and such things within the announcement, information of the observation or the object that they're talking about. Any relevant additional data if someone has like a light curve that they'd want to include, or there's I don't do asteroids, but say something could have a really interesting Minkowski drift. You don't want everyone to include that, but someone may want to include it in like a really specific case, so they can include that extra data and finally review things before submitting. And on top of that, we have our integration with Community Forum. So this is just a quick screenshot of what things look like whenever they're actually on there, where they can be filtered by topic tab. You can get email notifications, and of course, the important ability to have discussion about these announcements. This is kind of what things look like when they're actually on there. Our kind of final steps and future plans is we're finalizing the official policies. We got feedback on those from the people at the CADC to make sure that we're like in line with all of their rules. imminently. This is a warning to any working group leads in the room. We'll be sending you those for feedback very soon, and to make sure everything's happy within the community rules. And then kind of at the same time as this, we'll soon be doing a kind of introductory / recruiting session for reviewers or moderators of these rafts, so we can get people to sign up, because the bigger group we have of like reviewers and moderators, the quicker turnaround hopefully and these announcements going in. And if necessary, we can do a quick training session, but we're trying to keep everything relatively simple, so we can see if that's needed. And once we have a final list of reviewers, we can be in the full release, and hopefully people will be using the system at that point. So I'll just leave you here with my summary slide of the general bullet points of what we have, an example of what like the review page might look if you were put in a RAF submission, and various contact emails. If you have additional questions, you can feel free to email me, or if you don't want to talk to me, you can email these other folks here. And yeah, thank you.
I have 2 questions.
Thanks, Laura. This is Henry. It's great to see everything getting close to the end. I have 2, maybe hopefully quick questions. You mentioned future plans, but didn't put a timeline on it. So I was just wondering what what that was, or what your best guess was. And yeah, go ahead.
I was nervous to put specific dates on that if I didn't meet. The plan in my head is ideally everything should be getting done in the next couple of months, so by the end of the summer. But I didn't want to put a specific date on the slide in case anything got a bit
Understood.
Yeah.
Yeah. Okay. Just wondering. And then the other question, we haven't really discussed this, but now that you're getting close to the finish line, I was wondering if you had plans, or if you had thought about integration with ADS. Like, have you been talking to them about getting indexed in there and all that with the DOIs?
Yes, I can't remember the details. I don't think we've specifically integrated the DOIs with ADS, but the DOIs, because DOIs themselves are not like part of ADS but can be included. It's something we can maybe talk about after, because it definitely came up at the start when we were discussing things, but then we got so down in the details of actually getting everything running that it's maybe fallen to the wayside at some point. So yeah, maybe email me about that later.
Okay, thanks. Thank you, Laura. Let's move on to Valeria Karuba, who's going to talk about extracting asteroid physical properties from the Rubin Observatory's science validation survey data.
Hello, can you please confirm that you can see my presentation?
We saw it, but it went away. Could you unshare and reshare?
Sure.
There, it's back.
Okay, perfect. So good morning, my name is Valerio Karuba. I'm going to talk about extracting astrophysical property from various Rubin science validation surveys, rotational period, color, and taxonomy. This is a work that I've been doing in collaboration with Sara Greenstreet, Maria Mastropietro, and my students and members of the group on machine learning applied to small body. So you may be familiar with the work by a derived light curve for Rubin phase 2 data, and which are characterized by dense sampling, complete phase coverage. You can get direct physical characterization for these objects. Science validation data is a bit different. We don't have dense sampling, we have sparse sampling. In many cases, we have incomplete phase coverage. And it's more difficult to get physical characterization. You need to have cross-validated physical characterization. So the idea behind this work was what can we actually obtain from sparse science validation observations, which have been very similar to what we are actually getting for some of the data preview to from Rubin. So here we created a wrapper code for this approach based on high-order Fourier and Fourier methods. We compare the results for the periods based on the two methods. And if the periods are compatible, then we assume that these are reliable period. We can obtain then rotation correct colors, as discussed several times in this session and yesterday by Dr. Kurlander. And once we have the rotation corrected colors, we can obtain information on taxonomy. So this is to give an idea. The high-order Fourier method is based on Fourier expansion of Fourier order from 2 to 6 in model rotation, phase angle dependence, and band offsets. While the Lom's-Gargol method is a fixed second-order Fourier method that shares periodic signal across all bands. So to give an idea, this is an example for which our method works quite well. This is 2026 DO13, which is an asteroid in the science validation data. We get a period of 1.88993 hours from the order Fourier and 1.9108 hours from the multiband Lom's-Gargol method. So there is an agreement beyond 0.6%. We consider these are a reliable rotation period. And then we can obtain the rotation corrected colors and proceed to taxonomy. So we simulated what happens with respect to sparse data. And for doing that, we created a model which is based on two parameters: the number of temporal clusters, which tells how many cluster observations you have for the given asteroids. We might be 2, 3, 4 or more. And the half width of this cluster, which is the fraction of the space that they covered. So we can see that a spare sampling, of course, increases period ambiguity. Usually in our sample, the Lom's-Gargol method remains most robust. So this is usually our easier period estimation to get than the high-order Fourier. But the agreement identifies a confidence solution. And once you get 3 or 4 number of temporal clusters, usually you get a pretty reliable preliminary rotation period. So once the rotational variability is removed, you can pass then to study the colors. Here you have the distribution in colors for 2026 DO14 and superimposed a typical D-type from the Sloan's digital survey. So meaning GREZ color measure consistency, and the reference spectrals enable taxonomic classifications. And in particular, here we Leo and Carré taxonomical scheme in the domain of GRE slope Imanov-Zib color. And once we have the rotation correct GRE color, we can get this the location in this domain. I can tell you what class is this asteroid. And you can see here there's a pretty good agreement between the classification by Lom's-Gargol and high-order Fourier. And this asteroid in particular should probably be a D-type asteroid. So sparse Rubin science validation observation can provide physical meaningful asteroid taxonomy, at least for some objects. And we did it, we analyzed a series of objects to test them. We also compare with published results in the literature when available. So we have tried to obtain 36 asteroid characterization in our sample, but there are many more that are being processed. Here we are going to show only the ones that are going to appear in the Practice Space Science paper, which is currently under review. We obtained 25 taxonomy classification, and this was the number of observation per asteroid, which was the order 280 observation plus or minus 180. So despite the sparse sampling, we are able to get a preliminary taxonomical property for some asteroids, which is good news. And then as a side project, we were also able to get a new rotational period for some of the asteroids in the Science Validation Service. In particular, we identified 21 new asteroids that are beyond the classical spin barrier of 2.2 hours. This is work is currently under review in research notes. They are consistent with cohesive body models. They have implied cohesive strength of span between 1 and 10 megapascal. And this demonstrates the Rubin capability to discover rare phase rotator and provide a basis for statistical study of asteroid linear strength with Rubin. So to conclude, we created an independent method to recover reliable periods from sparse Rubin science validation observation. Reliable periods enable consistent GRZ color and physical meaningful taxonomical classification in some cases. Preliminary comparison with the newly released EDP2 catalog shows that there are 14 objects within our 36 science validation sample that are already present, which provide a direct pathway for extending this analysis to ADP2. And developer should be immediately applicable to Rubin EDP2 and future LSSC research. So thank you very much for your attention. This is a work which is currently under review in Planetary Space Science, and the work from Maria Mastropietro et al. Is also been submitted to a research note last week. We are waiting for the revision. If the work is accepted, we plan to release our wrapper code on GitHub. Thank you. I will take question now.
Thank you. This is on. Okay, good. Thank you. This is David Trilling. I have a question about, you had the plot of slope versus I minus C. Those colors are very red. I'm surprised that all of your asteroids are that red. Have you removed the solar color before you made this plot?
Yes, we did. And this is might be a small number statistics. These are just 35 of the asteroids that we applied. But we consider as many of them appear to be on the S complex side, part of the objects that are on the types. But we have other objects that appear to be bluer. So this might be a question of the sample that we're showing here in this presentation.
So there's a question on Slack. Is there some kind of trustworthiness metric one can use to gauge how reliable a period or color might be?
Can you repeat the question, please? Is there
some kind of trustworthy metric one can use to gauge how reliable a period or color might be? Something that can give you a sense of how sparse the sample is.
Well, yes, we can. Our colors are based essentially on the rotation period determination. If you don't get enough data, you don't get essentially a very good period, and you don't get a very good color determination. So how reliable is the taxonomy? We compared the asteroids for which we find the taxonomical classifications with the one that are published. And I think that of now 9 of the 10 for which we have data, they are consistent with the previous data in the literature. Does that answer the question?
I mean, I think Wes Tracer had the question on Slack, so if they have another follow-up question, they can send it there.
Any other questions in the room? Then with that, let's thank Lario again. And move on to our final speaker, Carrie Holt, talking about follow-up observations, moving objects, FOMO.
All right. Hi, everybody. I'm sad that I couldn't be there in person, but I'm glad I'm able to attend virtually. Okay. Can you see this? Okay.
Yes.
Great. Yeah, so my name is Carrie Holt, and I'm an LSS TDA Catalyst Fellow at Las Cumbres Observatory, working with Tim Lister on a follow-up coordination website that we call FOMO, which stands for Follow-up Observations of Moving Objects. So what is FOMO? Many of you have heard this before, but I'm just going to try to give like a big summary and then mostly stick to updates. So it's essentially a centralized coordination website where we can coordinate follow-up observations between community members. We can also see an overview of different proposals and facilities that are able to be used for TOO observations of exciting new things. And we can also include tools to plan and optimize observations across facilities between people, having automated robotic facilities, and then also act as a single reference point for follow-up status and observation history of objects. So what has been observed, what is planned to be observed, etc. Which then allows for better tracking from alert, observation, data, publication. So our base is the Tom Toolkit. This is a software package built by LCO to basically allow for different projects and collaborations to coordinate their observations without needing a sort of high-level database software expertise, which is good because I do not have that. This is widely used, been used for supernova science, microlensing, ZTF targets, and more. So within the Tom Toolkit, they already have a way to ingest targets from Rubin brokers, from Minor Planet Center, and now JPL APIs. You can do automated observation scheduling on LCO, Gemini, SOAR, and Blanco. You can do observation status updates, and have data ingest from your observations. And they just recently released a V3 with new data services and data products. Does somebody have anything? Am I okay? I thought I heard something. Okay. Okay. They're currently working on support with the RSP and also more ESO support, and then newly CFHT support, and additionally working on a facility status. But so the team that we're working with is super collaborative, able to work with us to achieve sort of these shared goals. If there's things that we can contribute to the general template that other people can use, we're happy to do that. So some existing features already in FOMO, we can ingest single objects from MPC, from JPL. We can ingest classes of objects with different constraints and filters. And we can also, we also have ephemeris generation, which uses sort of custom code with Sorka plus some other things. And here's an example of that on the right. So some updates, some of these updates you might have seen a couple weeks ago at ACM, but there's even newer updates thanks entirely to Tim. So we'll get there. So we've added Scout ingestion. So basically we have a way to ingest NEOCP objects from Scout. It can refetch and store version changes to the object's metadata, including NeoScore and impact rating, because that changes. So this is hopefully going to be in our main code base soon. Here's an example of that query form. And the reason that we've implemented this is to support the Rubin TOO triggers for potentially impacting NEOs. So there was a meeting, Rubin TOO's meeting in 2024 and 2026, and then discussion with the community on sort of defining these filters for when we would want to trigger for potentially impacting NEO. So now we have a dashboard of Scout objects that are currently passing those filters. And we can also see stats over the past year showing how many have passed which filters and help us refine those filters. Another update is we've added a new calendar module. So we can support ingesting classical runs. So you can say, I'm observing on NTT, these range of dates, I'm observing on this, just the first half of the night. And it'll also calculate different observing parameters you might need, like sunrise, sunset, night, start, end. You can also do an auto sync of LCO SOAR robotic observation. So it'll start with showing your general large window that you requested. And then once it's actually scheduled, it'll refine to that specific time. Here's an example on the right for the Didymos Hera observations campaign. So you can see some NTT, Magellan, some not happening LCO 2 meter, and some happening ones. And related to that, we've also, building on that, we've created campaigns. So this is basically a way that you can have a campaign for a specific target list. So it could be for iRubin, it could be TNO candidates confirmation at whatever large facility. And basically anybody can add their observation runs to these campaigns. You just fill out your details, say whether you're open to collaborating with them or not, the status of the run, etc. So this then goes to the review queue for admins to check over and then make sure that we match the telescope site to the MPC code. So example on the right here, you see this is what you would put in to submit your observations. And then below you can see an example of an ingest of a pass through an Atlas observational campaign that was just a spreadsheet passed around. And so this is something that I know people have been looking forward to and happy that that is existing now. We've also been able to connect FOMO to ESO Phase 2 interface. So we can fetch and create basic observation blocks and easily add the generated ephemeris file specific to Phase 2. And we're always looking for feedback from ESO observers on what you might like. So just an overview of the current status. You can add targets manually, JPL query, Scout query. You can retrieve target data automatically from JPL Minor Planet Center. You can send robotic observation requests to LCO, Gemini, SOAR, Blanco, and ESO. And there's an ephemeris generation module and a calendar module. You can get automated status updates of requests when you submit those robotic observation requests. And so we have successfully manually ingested a target, sent an observation request, received updates on that request, and then received the final data product. So we have a start to end, very, very minimal success in that. Before we deploy, we want to make sure that we are able to add targets from broker alerts. They're able to do that in Tom Toolkit, but we need to implement that into FOMO, and with it being more solar system specific. And also retrieving the target data from brokers. Making sure we have our management of the different users and proposals with different permission types. And then I'd like to update sort of the front end design and maybe get a new logo. And it's really important to note that in the new feature additions, not just for the minimum product, but we plan to have many, many more helpful tools for planning observations. And we also feel strongly about making sure we have proper integration with manual facilities, especially with the amount of in-kind contributions of telescope time for follow-up. So we definitely are planning on doing that. So we're taking any feedback. If you think we've missed something or we haven't considered something, just please let us know. And we're also welcoming collaborators. So anything you think you contribute, you think might be good for the system, again, just please reach out. Awesome. And with that, I'll take any questions.
So you have a question on Slack already. Is the time added to the FOMO calendar just treated as a general pool time, or does the PI still preserve control of what actually gets observed?
Or time in what? Which way?
In the FOMO calendar. I think you said that there was time being added to the FOMO calendar. So
Maybe go on mute.
yeah.
Just chat.
Yeah, I can chat, but yes. Yes. I'll also look at when I have not a full screen of my slides. I'll check the Slack itself and maybe be able to parse it better.
Wes, can you unmute and ask the question?
Yeah, maybe. Hi, this is Wes. Maybe I don't understand the true purpose of that calendar you were showing, where a bunch of different programs get added to it. It looks like this is programs from a bunch of different people that get added in all at once, and so I'm wondering, when FOMO or someone decides to observe something, is that still under the control of the PI who provided the time, or what?
As far as what is like publicly shown, or
No,
is
as
that
far
what you
as
mean?
what is actually observed.
Oh, yes. Yeah, absolutely. Yeah. You can trigger it like through like FOMO, like you can submit observations through FOMO, but ultimately only the PI of the proposal and whoever they designate can do that for sure.
Okay, thanks.
Hi, Carrie, it's Henry. Thanks for
Hi.
all this. It's great. Do you have plans, or have you thought about like some sort of push notification system where if you have like a classical run coming up and you forget to check FOMO, you'll get an email if you're signed up for, whatever, new comments and things like that?
Push system, I don't think we have thought about, but we do. There have been requests, and we're planning, especially for like manual observations of formulating lists of like priority lists of things that should be observed. But it's probably more just going to be like an output from the system, not like a push thing. But we'll think about it.
So this is Melissa Brucker. Are you thinking of it kind of like how the IWAN campaign did, but better, where people wrote down on the webpage, we're going to look at, let's say, 3i on this day, and someone else is going to look at it. I guess YR4 was the best example. I'm going to look at it in January, and so is going to look at it in February, and someone else is going to look at it in March, and we'll put in the times and our cameras and stuff like that. Is that what you're thinking?
Yeah, for the that's what the campaign system is basically trying to emulate is this idea that we can all talk about when we're going to observe something and coordinate between each other. Yeah.
Great. I have a question in general for the speakers. If you haven't uploaded your slides to the agenda, are you planning on doing that? Just a suggestion. It'd be nice to see everyone's slides.
Any speakers who have not uploaded slides, please do upload
I would love
slides.
to, but there's a limit for the weight of the file, and mine is larger.
Can you send it on Slack?
Yeah.
Maybe sending it on Slack in the session Slack would be a reasonable equivalent.
Also, can you turn yours into a PDF instead of a keynote or something? I can't open it.
Yeah, I could turn it into. Yeah.
Thank you.
All right. Any other questions for Barry?
This is Stephen Gwynn. Is FOMO 100% focused on recovery as opposed to pre-recovery? Is there any pre-recovery element to this?
You're muted.
Yeah, this is mostly focused on active planning observations and coordinating that. We don't plan on having like a backlog of Ruben to look through for pre-recovery things, if that's what you mean.
It is. Thank you very much.
Mm-hmm.
So I kind of have a meta question, not just for Carrie, but for everyone before her as well. The number of services and useful data sets and various things that I would want to use and know about is growing. It's going to become, I mean, it already is kind of difficult to figure out where all of these things are. Do we have a way to keep even at a level of single Google Doc? Here's what people have done. Here's what's available. Here's what to use, so that I can give that to my virtual assistant to know about. And then when I ask, how do I do this, that ChatGPT tells me go to that service.
You should use your virtual assistant to make a single web page for all the things.
I think that sounds like a really good job for the science collaboration to have a, we've got a website with a lot of tabs.
And maybe the software working group.
It may be really good to kind of keep
Tim was nodding. So.
I think you guys just threw Tim under the bus.
I was already under that bus. That bus has been rolling for a while. Yeah, no, this is definitely something we've identified from previous sprints, is that, we need a single place where all of the existing projects are sort of written down with contact details, so we can point people at other people and get them to work on things and not duplicate things. So, yeah. We'll get to it. Or Claude will get to it.
Okay. I think we are 8 minutes over, but we've scheduled 10 minutes of extra time into the schedule. So two more minutes of general questions and or advertising undergraduate programs too. Let's give another round of applause for